All right, so welcome everybody to Hoon Academy Lesson 3. So in this class, what are we going to do? We're going to increase our understanding of Hoon's type system, and we're going to learn how to make more sophisticated types, which are called molds. Next, we're going to learn how to do logical decision making, which is an important part of any programming language. This is an important lesson, and we're going to write what starts to resemble real complex Hoon code. All right. So in last class, we went over quite a bit how to use Hoon's type system for atoms or single values, single numbers, right? We learned that auras are different ways of interpreting an underlying atom, such as a text or a ship name, and that auras cast to each other if they nest in a structure like this, right? We learned how to use the Cohort rune as a fence to make sure the result of a computation is a certain type. For example, here in this code, we have ket-hep, pat-ud, send-hep, add 1, 2. So we're calling add on 1, 2, and we're just saying the result of that has to be a pat-ud, otherwise don't compile this code. And it works. And we also learn how to use ketless, which does type inference on this first argument and does the same thing. So here it's going to say, I infer Zod to be a pat P, and I'm going to cast the result of adding 1 to 2 to that. And then you get West, the galaxy West, which is 3 underneath. And finally, we learn how to get the default value of an aura. So every aura has a default value. So like the default value of a power S uses ket tar rune. It's that. And there's also the sugar syntax. So this is all great, but as I mentioned, we've been dealing just with single values so far. And for general computing, you'll need types for more complicated structures, which are like tuples, lists, maps, and so on and so forth. A lot of these structures you might have dealt with in other languages. Hoon covers these with what are called molds. To use an analogy with chemicals, so if atoms are like, chemical atoms, like hydrogen and oxygen, molds are like molecules, more complex structures that can be built piece by piece out of atoms. So molecules can be simple, like the water molecule is pretty simple, right? Or they can be very big and complex, like a piece of DNA. And the same goes for molds. Okay, so when you're writing Hoon to create a mold, you're in what's called structure mode. Structure mode is when the Hoon parser is interpreting your code as a specification for a type, rather than directly writing something that is a value. So what do I mean by this? Let's look at an example. So let's look at this code right here. I'll put it in the chat. We're just saying, let me pin the face word to the text hello, and then return what's in the face word. So that returns the text hello, right? We can also add a bit of type information to it, like this. So we're saying, let me pin the face word, which I specify the type of this face should be a pat-t. The data it has is the text hello, and then I return word. And it just does the same thing, right? So it turns out this is actually sugar syntax for the following rune, buck-tiz. So the desugared version looks like this, buck-tiz word pat-t. So now we've seen these two different situations where we write like A equals B, like something equals something else, right? You can directly assign a face to a value, like word equals hello, like that. It's like a nice shorthand. And you can do this like recursively, right? You can say the cell A is the cell of word equals hello, num equals 2, right? In the last lesson, we learned that this is actually sugar syntax, right? For the ket-tis rune. And that rune takes a face and a Hoon expression and just pins that face, returns that Hoon expression with the face pinned, right? And if you recall, it actually does sequential stuff like this. So here we're pinning these cell of faces to the cell of values, and then just applies them all like that. Alternatively, we have this syntax we just learned here. We're saying word equals pat t, and that's actually something a little different. That's saying this word face has a certain type. So these two syntaxes desugar to different things. So this instance of it, where you're just directly assigning a face to a value, that desugars to ket-tis, and that's in what's called value mode. You're talking about values. Whereas here, where it desugars to this buck-tis, that's structure mode, and that's talking about types. You're writing code about types, not values. So the rune family for working with structure mode is the bug family, and we're going to learn several runes in this family. So let's go through an example of actually building a simple mold using structure mode. Okay, so suppose we're building a simple bank app on Urbit. So what's the kind of data we might want to represent for an app like that? We might want to have PAP-P and for everyone's identity, and we might want to say for every PAP-P, here's how much money they have in the bank, right? So we could have a cell of PAP-P and PAP-RS. So to make this type structure, we're going to use a new rune called buckcol. So buckcol, we've seen this a few times before. It takes an indefinite amount of children, so it doesn't have a limit. If you give it 2 children, it's going to create a type which is a cell of 2 things. If you give it 3 children, it's going to create a type which is a cell of 3 things. 4 children, it will create a quadruple, and so on and so forth. And you close this rune with a tis, like we've seen before. Okay, so let's make a new data type with this rune. So here's our code. It says buckcol, bucktis, ship, PAP-P, bucktis, money, PAP-RS, and then tis. So to parse this, this buckcol has 2 children here. Then if we parse this bucktis, this also has 2 children. Ship and PAP-P are its 2 children. Boom. So this is the one child of the buckcol. Next, we have this other bucktis that has 2 children. Grabs this money and this PAP-RS. Boom, this is one child. And those are the 2 children of this, and then we close it with this tis. So if you want to parse the syntax tree of this expression, looks like this, right? This right here. So 1 child, 2 child, and those have their subchildren. So let's keep this type structure in our dojo under the name bank account. So we've seen this syntax before, right? So this is saying, this is a dojo specific shortcut. Remember, this is not Hoon code. And this is saying, let's store something under the name bank account and let it be this structure that we're creating. So let me press enter there. So, all right, let's make sure that our mold building worked. So consider this cell of 2 things. It's just a cell of Zod and 1, 2, 3, 4, 5, 6.78. That should fit our structure, right? Our structure is something we said is a cell with a ship, a PAP-P in the first place, and a PAP-RS in the second place. So this should fit, right? Let's check that fits. So we can use the Cohort room just like we used it with auras. So here this bank account isn't an aura, but it's a custom mold that we just created, saying Cohort bank account, this cell of two things. And we press enter, and boom, we return ship equals Zod, money equals 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that's a success of this casting. For molds, we also have this. This is basically a struct. Yes, I believe so. Yeah, I believe that's correct. For molds, you can also sugar this Cohort, and it's actually this with this tick notation. Tick bank account tick. This cell, and it does the same thing. It's a little different from auras because if you'll recall, when we do auras, like if we do PAP-P, take PAP-P, take 1, 2, 3, it actually desugars to a double application of this Cohort. It desugars to first you pull it to the empty aura and then you cast it to PAP-P. So it's a little different there, but like functionally they're like basically the same. Okay, so let's look at this full line of code. Okay, so what have we done here? We just had the same code that we had here. This is the same code, except we just substituted our mold definition into the face bank account. All right, we just substituted that mold definition right here. All right. So what is happening when we run this code? So first, the Hoon compiler is going to check the first position in the mold, which is ship PAP-P, right? Then, so it says, okay, we specified this as PAP-P. Let me check the first position in the value we provided, which is Zod. It infers that Zod is a PAP-P and confirms that PAP-P nests into PAP-P, so it passes the check there. Then it looks at the second position in the mold, says, okay, so this is a PAT-RS we specified. Let me look at the second position in this value, in this noun. This looks like a PAT-RS, that's what we infer, and that nests, so that also passes. And after it passes all the checks, it returns the cell with the face attached. All right, I have an example where it doesn't work. So let's try the following code. Here we're trying to Cohort bank account the cell of the text hello and the floating point 1, 2, 3, 4, 5, 6.78. Right. So what is this? This is a PAT-T, right? This is a text string. So what's going to happen? We get an error. It says mint nice, need PAT-P. Bank account is saying we need a PAT-P, but we have a PAT-T here. This error message here is perfectly descriptive of what just happened. So yeah, we're seeing this cell, inferring that it's a PAT-T. We're checking the mold and we're saying that has to be a PAT-P, doesn't nest, and we get this nest fail. What does mint nice mean? You know, there's a lot of these cryptically named error messages, and I don't know like why it's called mint nice in particular. You might have to ask, like, we could ask one of the core devs and learn that. But basically, I've come to associate mint nice with this sort of a nesting type mismatch error. So yeah, good question though. One of the things about Hoon is that there's a lot of these like weird little 4-letter names, and sometimes that bleeds into the error messages, and they could be more descriptive for sure. Okay, so and this piece of code obviously isn't going to work either, right? So what's going on here? It's going to say, oh well, I guess not obvious, but when the Hoon compiler sees a number by itself, it actually infers pat UD, not just an empty aura, right? So it says, so it sees one, infers pat UD, says, hey, we're saying this first position should be a pat P. Pat UD doesn't nest into pat P, and we get this nest fail again, right? Need pat P, have pat UD. All right. Any questions on that so far? Okay. There's no questions. We shall move on. So if you see these sorts of mold definitions in the wild, you'll probably see them in a more readable way. We learned about sugar syntax last lesson, right? So we can apply sugar syntax to simplify this expression. So here's our original expression we just had. Let me pull that up. It's right here. It's a long expression, right? So first we can sugar this buck-tiz. Instead of having it in tall form like this, we just collapse this to ship equals pat P. We collapse this into money equals pat RS. And then this buck coal has a sugar form too. And we can just write it as a cell like this, right? And this final form is a lot more neat. Well, it's easier to read than this for sure, right? And just to show you, it does the same thing. There's that final form of the code, fully sugared, and you get the same result. But there's some subtle traps here. We have to be careful, a little careful doing this. So suppose that I wanted to use this when I was defining the bank account hold. So like here we're saying tisfaz, let me assign the face bank account to this structure right here, right? Here we sugared this buck tis, but we haven't sugared this buck coal yet, right? This is still tall form right here. So this is our code, right? We're doing the same thing. We're saying let bank account be this, cast this structure to bank account. But if we want to sugar this here, we need to use a slightly different syntax. Let's see what happens in our naive. So if we do this, right, put this in a cell, then we do this, you get a failure, right? We actually need to use a slightly different syntax. Have this comma right here, this comma in front of the cell. There we go. Like this. And now it works. So why is that? So yeah, here's what we did. Why do we have to do that? Yes, com signifies structure mode, right? Ranesh Rubit is reading ahead a little bit. So this tisfaz bank account, this usually expects a value here. This usually when you use this, you're saying bank account is the number one, or like a cell of the number one and the number two, or whatever, you know, like it's usually in value mode. But here we're saying, actually, we're going to use this to define a structure. Since that's not the usual use of this, we have to specify, we have to differentiate this. We have to make it clear to the compiler we're talking about a structure, which is why we have this different sugar syntax. Like usually you use TISFAS like this, right? Like use TISFAS numbers, let numbers be the cell of 1 and 2, and then return numbers, right? That desugars to, as we've learned, the Cohort rooms for making cell, right? Numbers, Cohort 1, 2 numbers. Same thing. So when we put this com in front, that's saying, hey, this is a cell of 2 structures. We're making a structure here. We're not talking about values. And then that makes it clear that this desugars to bug col, not Cohort, right? How is TISFAS Rune able to take arguments in both structure and value mode? It just is able to. That's how it was designed, but you just need to differentiate the 2 cases, and this is the syntax for differentiating. Now if we go back to how we're using this with kethep, this kethep expects structure mode. When you kethep something, that first argument is always going to be a type. You're always, because this rune is about casting it to a type, right? But this is always going to be type. So there's no need to make that differentiation. So you can just use cell here. We can use a cell here. And at first glance, these 2 things look kind of similar, right? But there's actually different runes underneath. When you run this, it's going to work. All right. Yeah. Any other questions on that? So one more place that structure mode can show up, kind of interesting, it's a useful little trick, is you can actually use structure mode directly in this, in the first argument to the TISFAS. So what's going on here? So usually this TISFAS, how we've seen this before is like, there's just something, like some singular name here, right? We're saying, let bank account or ship or like numbers, whatever, be this thing in the rest of this code, right? Here we're actually doing a double assignment. We're using structure mode here. We're saying, let the structure of ship equals pat p and money equals pat rs be the value of zod and .123. With that, just return ship. And we get zod, and we get money here as well. So, and this is structure mode. Whenever you're just talking about faces, the compiler doesn't know you're in structure mode. TISFAS expects just the face in its first argument, so it expects a structure mode thing. So this desugars to the bug col room. Bug col ship equals pat p, money equals pat rs. Same thing. All right. Okay. Let me show you something interesting we can do. All right. What happens if I run this code? Everyone see that? Do we recall what this first rune is? Thanks, Roberto. Do you recall what this first rune is? We've learned this before, right? Senhep, yes. What does Senhep do? Calls a gate. Yes. Senhep invokes a gate on its arguments, right? So what does that mean here? This is a bank account is a mold, right? Bank account is still stored in our Dojo state. This is a mold we created, and we're trying to use it. This looks a lot like what we were doing with kethep before, but what happens if I press enter here? Boom, it returns something. Return ship equals daspelf bigreg famtol and money equals this. So what's going on, right? We just tried the same thing with kethep instead of SenHep, and that failed, right? Yes, yes, correct, Franklin. Type coercion, that's where we're going. So it turns out any mold is also a gate and can be called as one. And that gives you different behavior than casting the mold with CatHep. So recall that when we're using CatHep, we're doing element-wise checking to make sure every position in here matches every corresponding position in the mold. When we call it as a gate with SenHep, we're treating this data as raw noun, a raw knock noun, just the numbers underneath, with no type information whatsoever. And then we're coercing that underlying data to fit this mold. So we could have even done this on 1, 2. That didn't work before. SenHep bank account 1, 2. 1 is the number underlying NEC. Money is, or this tiny number is the floating point of 2. So, and we could have used this sugar syntax here, right? Here's this sugar syntax, which we learned last lesson for SenHep. Boom, same thing. All right. What if ship value cannot be coerced to PEP-P? That's a great question. We are getting there. So these two different usages of molds are respectively called casting and molding. And their differences are illustrated in this graphic right here. So casting, use CatHep, you check the results of your Hoon element-wise, see if it fits with the mold. It crashes with nest fail, there's a mismatch. And this occurs when your code is compiled. So this is a faster operation because they just check it when you compile the code, when you're building the code, rather than every time like a user runs it. And if you have a type error, if you have a mismatch here, it's going to catch that when you're compiling the code, when you're building the code, when you're releasing it, not when the user is using it, right? Molding is different. We're taking the result of this, just taking the raw knock, coercing it to fit this mold, and it happens at runtime. So this happens every time the code is run, if this is in your code, and this can cause runtime errors. So to see what we mean with this, let's try to mold something that doesn't fit. All right, so Ronis Rugwit just asked, what if you can't coerce something to something? So we know that bank account is a structure with two things, right? But here we have a cell of 1, 2, 3, which we know of a cell of 1 and 2, 3, like this, right? So here we have something which is an atom in the first place, and then a cell in the second place. But bank account is, it wants something that's an atom in the first and second place, right? So how would you even make this into an atom? You can't, right? And we're going to get a Hoon expression failed. So whenever, if your attempt to call your mold as a gate fails, you're going to get this error. So in short, casting is used as a fence throughout your data. It makes your code safer. It makes sure that any data that gets past a certain point must match a particular type. And it catches things when the code compiles. Molding is an active action to force some data to fit a type. And they have different uses, and you might use both of them in certain situations even. So yeah, any questions on casting versus molding? All right. So we've been using Buckhole, just our Buckhole room, right? We got a lot of mileage out of that. But there's one more room that we can learn for making molds. Turns out these two rooms is pretty much all you need. for most molds. Suppose that for whatever reason you want to make a type that is either a text or a floating point number or a date. So we're saying it's one value, but it can be any of these three things. This is what's called a type union, and you create it with this room. It's called buckwhip. So like buckhole, it takes an indefinite number of children, but it's just saying it can be this thing or this thing or this thing. So let's try an example. Let's pin our what we call new type. There's a buckwhip of pat t, pat rs, pat da. Close that room with this tis. All right, boom. So let's take it for a spin. Let's see if it works. So if we say ket hep new type, this type union, and we give it a date, it's going to work, and it's going to return that date back to us. Right? And if we give it like a pat p, it's going to say there we need something that's a pat da or a pat rs or a pat t. We have a pat p. Now there's a little bit of a weird quirk because this should allow the text hello, right? Because that's a pat t that's in the type union and does allow it, but it defaults to formatting it as pat da, which is the last thing in the type union. If we give it a pat rs, it's also going to allow it to pass, but format it as a pat da. So that's a weird quirk of the type system. So in practice, you don't actually use this with auras like this. They're most commonly used with the pat-tas term constants that we learned in the last lesson. So what are those? We should have learned that a term is text which is of type pat-tas, and it's also a unique type in and of itself. So like this, right? And it starts with this sen. Okay. So let's make a new type union. So I'm going to pin to the dojo this reptile type, which is a type union of sen snake or sen lizard or sen crocodile. And we could have written this in the sugar syntax, right? Same thing, where you have this sugar syntax, which is just this what around these parentheses and your type arguments, right? Same thing. All right. So to use this type, we can say, let me cast sen snake to a sen reptile, and it passes. Sen snake is indeed in this type union, or with the sugar syntax of ket hep, sen snake, right? And we can check that sen elephant does not pass this. We have sen elephant, need sen crocodile, sen lizard, sen snake. And we can do what we just learned, and we can call this as a gate. So here we're calling reptile as a gate on this big number. Now what's going to happen? You get sen lizard. So this is the number that is underlying the text sen lizard. So you do this, you get sen lizard back. So that's why this worked. Here's the sugar syntax version. And if you call it as a gate and the underlying number doesn't parse to one of these things in the type union, like the number 1, you get a failure. Any questions on type unions so far? All right. So suppose that you're a fan of reptiles, you're running a reptile care facility, and you need to keep track of how much you're feeding your different reptile pets this week. So to create such a data structure, we can combine the runes that we just learned. So in case you haven't pinned these, you can pin them again. So here's our reptile structure, which is a type union of these three, right? Let's make a new structure called reptile tracker. Here we're saying reptile tracker is buccal cell type, which has species equals reptile in the first entry, and meals equals PAT-UD in the second entry. So here we're calling upon a type that we just defined. So this type is using another custom type in its definition. Okay, boom. Now, certainly a cell of send crocodile in 3 should fit this type, right? Call it with pethab, and yes, indeed does fit. It returns the structure with the faces attached. And we can also call this custom structure as a gate senhep reptile tracker on the cell of a big number and 4. And that gives you species equal lizard, meals equals 4. So this is a pretty simple example of combining a type union with the buckwhat and a cell type with the buckcol, but you can combine them with as much complexity as you want. You can use these things with each other however much you want. For example, you could use buckhole inside a buckwhat to get a type union of different cells, right? You can get a structure which is a cell of different cells, and so on and so forth. So these two tools really give you enough power to make any mold you might really encounter in a day-to-day basis. We're excluding recursive molds, which we'll learn about later, which is like something that you don't know how many entries it has. But you're building an app, if you're making some data tracking structure, like this will buckhole and buckwhat really does a lot for you. Okay, so just like with atoms, we can get bunts or default values for all the molds we just created using the Ketar. So for a cell type, it does what you expect. It's going to get the bunt for each part of the cell and just return those things in the cell. So recall the bank account structure type we created. If you do Ketar bank account, it's gonna say what's the default value of PAP-P, Zod, what's the default value of money, and it's gonna return a cell of those two things. And we can also use the sugar syntax here, this tar bank account. If you have a type union, it defaults to getting the bunt of the last type in the union. So recall we made this new type structure, which is a union of PAT-T power S and PAT-DA. And if we do Ketar new type, get the default value, it's going to get the default value of PAT-DA. If we have a type union of terms like reptile, Ketar reptile, going to give you crocodile, which was the last one in that triple. And if you have a combination of a cell of a buccal and a buckwhat, does what you expect, goes into here. That was a buckwhat of reptile, and it gets crocodile, and it gets meals equals 0. All right, any questions on that so far? All right, so that concludes our discussion of molds for today. Now we're going to pivot into a different topic, which is decision making. So in computer programming, making decisions is based on whether a condition is met is a really fundamental and important part of programming, right? if this, then do this, else do that, right? We may be familiar with such logical branching, right? Hoon has a family of runes for doing this, which are the what runes. They're pretty straightforward to use and understand. So the first rune we're going to learn here is called what call. This is the most fundamental decision-making rune we're going to learn. So it takes 3 children. The first child is a Hoon expression that evaluates to send.y or send.n. And if this is a send.y, it's going to evaluate this second child. To send.n, evaluate the third child. The simplest possible usage of this rune will look like this. We're saying what call send.y. Since the first child is send.y, we take the second child, which is the number 1, and simply return 1. And we can do what call send.n, which is going to make us take the second child and return 2. All right. Pretty straightforward, right? So to learn some more sophisticated uses of this, let's learn some comparison operators in here. So basically, these are standard library gates that work how you'd expect. They allow you to compare 2 atoms to each other. So, for example, is 1 greater than 2? No. Is 2 greater than 1? Yes. Is 10 greater than 10? No. Is 1 less than or equal to 2? Yes. Is 2 less than or equal to 1? No. We can even compare things with type information, because this just compares the underlying atom. So is Zod less than or equal to West? Yes, it is, because this is 1, or this is 0, and this is 3. All right. We should also recall the .tis rune that we learned before. So this tests if 2 nouns are equal to each other. It also has a sugar syntax that looks like this. Okay. So we can do equals 1, 2, or tis 1, 2. No. Tis 2, 2. Yes. It's going to work for cells. So tis 1, 2, 1, 2. Yes. And it also disregards the OR information. So this number is the number which underlies the text hello. It's going to say yes, these are equal. And if you put those in cells, the cell of 1 and this big number, cell of 1 and hello, I'm going to say yes. So let's go back to comparisons. So we can take all these and put them into our what call room, right? So let's check out this code. Here we're saying pin x to the value 3. If x is greater than 2, return the text x was greater than 2. Otherwise, return the text x was not greater than 2. And we're going to get x is greater than 2. And if we change x to 1, or sorry, change x to 2, you get it was not greater than 2. Change x to 1, it was not greater than 2. Does everyone understand the logic that's going on here? Just assigning x to a value, and we're calling this comparison gate on x. That returns a Boolean that becomes the first argument to this what call. And yeah. You'll most commonly see this in the sugar syntax, which is like this. Here we're sugaring this gate call. So assign x to 1, what call the result of calling gth x2. That becomes a Boolean, and that lets you decide which of these branches to take. And you can put further logic in here rather than directly returning a value. So here in this code, we're saying, let me pin x to 1. If x is greater than 2, calculate mul x5. Otherwise, to calculate add x1, 1 is not greater than 2, so we're going to calculate 1 plus 1, just 2. All right. So I'm going to use the restroom really quick. Be right back. All right, thanks for waiting, guys. All right, so we just did comparison operators, right? Comparing two numbers, getting a Boolean out of it, and using that to make decisions. So we can also do other things with our Boolean or Loopian values. So Hoon has the equivalent of not, and, or. So these logical operations that are very fundamental to programming, right? The rune for not is WhatsApp. So it takes one child, just some Hoon that evaluates to send.y or send.n, and it has a sugar form like this, which is zap, the argument. And it just takes that send.y or send.n and just returns the opposite of it. So most simple usage looks like this. WhatsApp, send.y, send.n. WhatsApp, send.n, send.y. WhatsApp is 2 greater than 3. That should be a no, right? So this is going to reverse it and return a yes. And the sugar syntax looks like this. It's nice and short, just this zap in front. So the rune for logical and is what Pam. It takes an indefinite number of children, as many children as you want to give it. Each of those should be some Hoon that evaluates to send.y or send.n. And it's going to take all those. If all of these evaluate to send.y, this will give you back send.y. And if one of them or more is send.n, you get a send.n, right? So here's the simplest example. We're saying what Pam, send.y, send.y, send.n, and send.y. So there's just one no in here. That's going to make the whole thing no. If all of them are yes, then we get a yes. And the sugar form of this looks like this. So we just have this Pam, put in the parentheses, and we just put all our arguments in there. So you can already start to make more complex expressions with this. So here we're having an and. We're saying, give me a yes if all of these resolve to yes. What are the three arguments to this sweatpan? We're saying, first argument is 2 greater than 1? Yes. The second argument is 3 greater than 2? That should be yes. And the third argument is the reverse of if 4 is greater than 3. So this should be no, right? And then, as you expect, whole expression evaluates no. We get rid of this reversal, we get a yes, because all these three substatements are true. So the whole thing evaluates true, right? Any questions on that? And here's the sugar version. It's a bit shorter, just ham in front of these three expressions like that. Are there flow control tricks you can do with this, like in C? I think so, but I'm not too familiar with the expressions in C. Oh, I saw some people saying they're stuck on some of the exercises. If you are, please definitely reach out to me. Number one, I can help, and also I like hearing feedback on which questions are easy or which questions are making people stuck. That helps me make the lessons better for you guys. So yeah, definitely just tell me hey, this question tripped me up, or this question took a while. Yeah, your feedback has been helping me, Roberta, so I appreciate it. All right, so there's a rune for a logical and. There's also a rune for logical or. You guys know logical or. It says if at least one of these is a yes, then the whole thing is yes. If all of them are no, then it's going to be a no. So the simplest usage of this is going to be like this. What bar? No, 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 no. You get a no. What bar? No, no, yes, no. And you get a yes. The sugar syntax looks like this. It's just a bar in front of the parentheses and then all the arguments in there. This is just the sugar version of this statement. These two are the same. And now you can make more complex expressions. So we're saying what bar says if at least one of these gives me a yes, then the whole thing is yes. So is 1 greater than 2? No. Is 2 greater than 3? No. Is 4 greater than 3? Yes. The whole thing gives you yes. And here we can sugar this expression like this. This bar, parentheses, in front of these three. Too many spaces. There. Yes, if you guys want to start studying together, I 100% encourage that. And yeah, hang out. The best way is to hang out in the gather town. All right. So those are our basic Boolean operations. We can also make decisions based on information the type system knows. This is something a bit more subtle here. So the what sig rune branches on whether this first argument reduces to sig, whether the compiler knows this is this reduces to sig. Or sorry. Yeah, I'll explain it a bit. So this takes 3 children, complete Hoon expression. If child 1 reduces to sig, evaluate this, otherwise evaluate this. Okay, so let's look at this code right here. What's going on in this code? So let's assign A to sig. And we're saying what sig A. So this what sig says if A is sig, do the first branch. Otherwise, do the second branch. Or sorry, the second and the third. And this is like a very, very straightforward piece of code, right? Based on how I just explained this works. But actually there's a problem here. And if I run this, it's gonna fail with this mint vain error. So this code right here, let's look at that. We're just assigning A to sig, and we're branching based on whether A is sig. So what's going on? So this character by itself, the sig, is its own special type in Hoon. And because of this, the Hoon compiler is reading this and saying, I know that this is sig. Therefore, I know that this what sig is always going to take this branch. It's always going to do this. It's never going to do this based on the type information I know. And whenever the compiler knows that you have a switch statement and there's a branch you can never take, it's going to give you a mint vain error. So that's what this means. This mint vain error means if this mint vain error means if there's a branch that you can't take, it's going to give you that. So March Osteen says no if not A. You can do if not by just combining what col and what zap. So you just do this what zap, right? That's not, and then you put that in the first argument of your what col, right? So, yep. What's the value of sig again? Sig is just 0. So it's like a type overlay over 0. So there we go. Yeah. So how can we confuse the compiler and make this piece of code work? Let's do it like this. Okay. Let's assign A to casting the sig to a pat UD. And then do the same thing, right? If A is sig, do this, otherwise do this. And boom, we get it was null. So why did this work? When something is a pat UD can be anything. It can be a 0, 1, 2, 3, 4, 5, 6, 7, 8, so on, right? That means the compiler does not know that this is a 0 necessarily. And it'll let you, it says, okay, these two branches are a possibility based on what I know. And we can just even directly use a number. So set A to be 0. What's sig A? It was null or it was not null. It was null. Okay. And we set it to 1. It's going to say it was not null. So it is like a subtle little thing, but a mint vain error is something that pops up and sometimes can confuse a Hoon coder. So I figured it was good to spend some time and understand this. All right. So decision making based on types is a very important theme in Hoon. And there's more powerful ways that we can use this. So recall that earlier we made type unions like let reptile be the type union of send snake, send lizard, or send crocodile, right? And that to the dojo. And there's a rune that we can use to work with these sorts of type unions. It's called whathep. Also, I'm realizing that we are now at 1 hour. I think we're going to be about 5 or 10 minutes over. I apologize for that. So thank you guys. And if you have something, feel free to drop out. All right. So we have this type union. Send snake, send lizard, send crocodile. And we can use it with this switch statement with this whathep rune. So what does this rune do? It takes an argument. It says, if that argument is this type, then do this. If it's this type, then do this, and so on and so forth, as many pairs as you like. So let's see an example of this code. So here's this code. Put it in the chat. So here we're saying, here we're just redefining our reptile to make this complete. But we're defining the type. We're saying let R be an instance of reptile with value lizard and also type lizard. And then we're saying we're switching on the type of R. If R is a send snake, return the text, I'm a snake. If it's a lizard, return the text, I'm a lizard. And so on and so forth. So if this, then do this, if this, do this. So let's run this. And it's going to return the text, I'm a lizard, because R was send lizard, right? And of course, if we change what R is, we change it to send snake, it will take this branch and the switch statement instead and return I'm a snake. If we add an extra branch to this code, if we add a send turtle, I'm a turtle, well, send turtle isn't part of this type union. So what's going to happen? It's going to give us something we just saw, which is a mint vein error. So this mint vein error is because the switch statement has a branch for send turtle. The compiler knows that reptile is just send snake, send lizard, send crocodile. It knows this branch will never be taken, and it gives you this mint vein error. Any questions on that? So this is just a rune to switch on the type of something. Whatever the type is, you define a different behavior. So the what lust rune is just like the what hep rune, except you also get to define a default behavior to perform if these other cases don't match. So let's see an example. Here we're defining animal to be a type union of send bird, send bat, send cow, send sheep, and send rabbit. Let's define an instance of animal with a face A and value and type send cow. We're switching on the type of A. If these other cases don't match, evaluate this. If the type is send bird, evaluate this. Type is send bat, evaluate this. So what happens when we run the code? Send cow results in this default branch being taken because it's not defined here, and it returns I cannot fly. And if we change it to send bird, it's going to return I can fly. Right, that's taking this branch right here. There's one more stylistic trick we can learn. This little shorthand right here says define an instance of animal with face animal. So this is like if you just define a type and you want to make an instance of it and you don't feel like coming up with a new name, you can just do this. And so what does this do? This equals this tis animal send cow means that if we call animal, it's not going to grab this type definition. It's going to grab the most recent definition, which is an instance of animal with face send cow. And if we did this, if we try to grab this original definition of the whole mold, it's going to return something different. It's actually going to take a long time to evaluate. It's going to be this huge thing. So we'll learn why this is a huge thing, because molds are gates. This will be in a future lesson. But the point being that when you do this, this makes an instance, and that becomes the local definition of it. All right. So one last thing, really quickly. We are finally, Ranis Rugat seems like a bad practice to use the same name. It can be confusing, but the good thing is that in Hoon, both this local animal and this this type definition are both preserved. So if you do like cat animal, that lets you grab this original one, and if you just do animal, that grabs the local one. So it can be a little confusing because you're right, because you're confusing something that's a value and something that's a type. But people use this shorthand when they're writing apps, and it can help for that because often you're making a type and you just have like one instance of it that you're using. But yeah, we'll talk about that later. So super short discussion on style. So with this lesson, we're finally learning how to write bigger and more complex pieces of Hoon. So we learned that spacing Hoon code, that we only need to differentiate between one space or two or more spaces for technically correct Hoon code. So if you have a piece of code like this, what col send.y, 1, 2, right? We saw this. This is just saying if send.y, return this, otherwise return this. We're going to get this one. We could also format it like this, like everything on a new line does the same code. Or even we can do something bizarre like this, like that looks awful, but it's the same code as this because two or more spaces all the same, right? However, for every rune, there's a standard, neat way of formatting the spacing and indentation. So let's check the docs site. We just looked up what col on docs.urbit.org. It says tall form should look like this. What col PQR should look like this. So that means the proper way to format this expression looks like this. Boom. That's much more readable, right? So like with our what have, the switch statement over reptile, we could have done something obscene and like put this whole, we could have put this whole switch statement on one line. That's technically correct Hoon code, but it's horrible to read, right? You can't tell like where are the pairs. It's hard to tell. So it works, but if you go to the docs for what have, say, oh, I'm supposed to write it like this, right? And that gives you this neat formatting like this, right? Much better. Okay. So for the homework, you're gonna start working on these bigger pieces of code. You're still working in the dojo, but a useful tip at this point is to write your code in the notepad or write it in a code editor while you're working on it, then copy paste it into the dojo to see if it works. That way, like you're not just like composing lines and lines of stuff in the dojo. That's a bit tougher. So, all right, that brings us to the end of the lesson. Thank you all for your patience. Is there a lint on save option for VS Code plugin? I'm not exactly sure what that is, but please DM me about it after the class. All right, yeah, let me end the recording. I'll take time for any questions you guys might have.